So we're going to conclude with this, with the last talk. So we apply Weber-Roda's law, which says that we keep the best for the last.
Again, about harmonic measure or elliptic measure. I remind you with my big pointer that you know, a harmonic measure, the simplest description is you start from point X in the middle of a domain. The precise point doesn't matter. You send a Brownian motion, and then eventually a Brownian motion leaves the domain, and you compute the probability of living through a given set A or not. And the probability of living through a given set is what I denote by omega x of A. All right. Okay. So the things that we've been playing with for a long time are questions that say, if your domain is nice, you would want to know that the harmonic measure has nice properties. And if you're lucky, try also to go for converse results, but say that if a harmonic measure is nice, then the domain is nice. And by nice, I mean essentially proportional to some given measure that you have on the boundary, for instance, surface measure in this picture. So I will say that harmonic measure is nice when the chances of exiting through a set are essentially proportional to the size of a set measured by surface, right? Okay, so that's nice. And again, you want to know whether the geometry of a domain is related to this nice property. Okay, so same question. So the answer to this has been known for now some years. There are many theorems, but the general idea of the theorems is that rectifiable sets are good for harmonic measure. So rectifiable sets are, so here I drew a complicated rectifiable set. Essentially a smooth curve would be in dimension 2, would be good enough. And at the opposite, things that are called totally non-rectifiable, they're supposed to be bad. And I have one example of a totally non-rectifiable set, which is a Cantor set. So the size of a Cantor set is the same as you know, the size of the other set on the other side. It's just that its shape is different. But this guy has a length which is also of the order of 1. Okay, so that's the. Okay, one last thing. This is what happened also when we tried to look at different boundaries, and in particular boundaries which have lower dimensions, so very, very small boundaries. Or just a simple example would be you have a domain in R3, but then the boundary is a curve. You have everything except for a curve. Okay, and in fact, for those things, the good operators that are supposed to replace the Laplacian are the operators L written in blue. So Brownian motion, as I've been talking about it so far, is associated to the basic operator, which is called Laplacian, which is the simplest one. And then here, the operators that we would be looking at would be the simplest modifications that we can think of a Laplacian. So you take the divergence of a function, you multiply by a scalar function A, so it depends on the point, but it's not a matrix. Then you take the divergence of this, and then you get this operator, and you're studying solutions of this blue operator as opposed to harmonic functions. Okay. So I'll say that A looks a little bit like a way to modify the geometry of your domain. And in particular, since you've been knowing about the Agman distance functions, essentially the way you change the geometry is by saying that the length of paths, instead of being just the usual length, when you go along the path, you multiply by the function A or some power of a function A, and you get a different length, a different distance between points. And the operator associated to this distance is this operator L that I'm talking about. So in the things that we've been doing with large codimensions, A was looking like a smooth power of the distance to the boundary. In the examples that I'm going to talk about now, in fact, A is equivalent to the distance. It's just a little twist on the geometry. Okay. Don't hesitate to ask questions. It's true that I feel a little bit lonely. Okay.
We are all ears.
So again, the typical result, okay, very good. So the typical results that we have is that when omega is a nice domain, and typically it means, for instance, uniformly rectifiable, then we can say nice things about harmonic measure, essentially saying that it's roughly proportional to surface measure, for instance, okay? And in the other direction, it was known that the absence of rectifiability, so for instance, the behavior of a Cantor set would be bad for harmonic measure, okay? But apparently we're lacking counterexamples. So we know that the Cantor set that I was talking about before, and I'll draw another picture of a Cantor set later. But the Cantor set is an example where the harmonic measure is not absolutely continuous with respect to the standard measure on the set. I have to say that it's a reasonably subtle thing. There is a theorem saying that the harmonic measure is living on a set of dimension 1. This Cantor set is of dimension 1, and it just happens that the harmonic measure is living on a small set in this Cantor set, but I would say barely. It's not, it's rather hard to prove that harmonic measure is bad on Cantor sets, okay? And the question that I'm trying to answer it comes into two flavors. The first one is, are there elliptic operators of a type divergence with a matrix A for which precisely the best Cantor set that you can think of? Are there elliptic operators for which this operator is actually nice instead of being bad? So for instance, A would not be the identity, L would not be the Laplacian. It's just, okay, can you try to find an operator which is adapted to the Cantor set so that harmonic measure becomes nice? And my second question, which is the one I prefer to some extent, is can you even choose elliptic operators of that type which are of the form divergence times some scalar function times gradient, which means the geometry is essentially perturbing the distance? And the answer is going to be yes. And okay, we'll go. Okay, so I have a few comments and then I show pictures. Okay, so the few comments is again, as I said before, when you try the Laplacian, it doesn't work, but it's actually not so easy. And for instance, there are many Cantor sets for which it was hard to prove that harmonic measure is not absolutely continuous with respect to length measure. The second thing that I'm going to start talking about is green functions. So the green functions are functions on the domain, which has the property that they're positive and they tend to 0 at the boundary. And if you know green functions well, you know the harmonic measure well, but usually it's not so easy to use because green functions are hard to compute, okay? Nonetheless, there is something funny about doing counterexamples, is that if you choose the green function and you manage to find an operator that corresponds to the green function, then you're happy because the green function, if it's equivalent as in the examples to the distance to the set, then you will know easily that the harmonic measure is nice. So in other words, here we're having a bad set, and if we can find a function, a distance function to the boundary, such that it is L harmonic for some right operator L, then we win, okay? And again, to me, it's a nice surprise because usually, again, green functions are making me afraid. So I'll draw pictures now. Okay, so this is step 1 in the construction of a Cantor set of dimension 1. So it's the most standard Cantor set. This is step 2. So you replace corners by smaller corners and so on and so forth. In fact, the Cantor set at the end is going to be the little dust that you don't see. All the intermediate straight lines here disappear from the Cantor set, just used for computation. Okay. So now I'm trying to draw level sets of a green function, and the green function is going to be in green. And the gradient lines are in red, and they're, if I do it correctly, the best would be that they are orthogonal to the green lines, okay? And I draw it in a basic square region, which is here, and even only half of it, because afterward by symmetry, we're going to be able to do something like this. So essentially here, I draw those things with my bare hands, right? The green things here and the red things here. This is the complete picture after the symmetries, okay? So I decide this has to be the function. I decide the function has to have a fractional nature so that in fact, you should glue exactly copies of the pictures that I had here in the middle, and you get a picture like this, okay? I'll draw another, so this is another picture, a little bit more smooth. You do exactly the same thing, except that the regions are different. You draw the red lines first, then you go over green lines, then you complete, then you have 4 pieces that you'll put in the 4 corners, and you get something like this, okay? So there is a proof here. The proof is that you have to be able to draw all those curves in such a way that they never get too close to each other and never get too far from each other. And if you can do this, then you have a green function which satisfies the equation for some operator, and the operator has some good control about it, right? But I think I'm probably, yeah, probably I'm finished by now, all right? So I'm open to all questions about it.
Okay, thank you, Guy. So the talk is open for questions. So I have one, if there are not. So I jump that on my position as chair to ask a question. So it means that the harmonic measure here, is it what you call nice or not? I mean,
no, in this case, it's nice. So
it's nice. It means that, so, okay, tell me if I'm wrong, but it's like a physics understanding. It's like if you were in, you follow this harmonic measure as always these random walkers that are following this operator for diffusion. That means that you can reach, although that you have the dust, which you have inner points and points that look like outer points, you can always reach the inner points, how deep they are inside the structure. Is that true?
So the design is that within 2 constants. So again, it's
okay.
So, you know, it's a little bit like, you know, you're going to play, I mean, it's an analogy. It's not true, right? You're playing golf on this field and you try to aim at the Cantor set. And then you put little bumps on the golf field so that the Brownian paths or the golf balls will go in a slightly twisted direction. And in principle, the result of a story is that when you aim at any point on the Cantor set, you have equal chances of getting it.
That's fantastic.
Right? So in other words, you know, there is a little bit of wind, but takes the Brownian path away from the corners so that it has a fair chance to go in the you know, in the hidden parts. Right?
Okay.
And again, I mean, the point is that you, instead of constructing something clever about the Brownian paths and trying to attract them somewhere, you just decide brutally what is the green function, which amounts exactly to the same thing. And if you can find a green function which is acceptable, the operator will just have to do, you know, what the green function says.
Okay.
Right.
I have other questions, but I will stop here because maybe other people have questions.
So I have a question. This David. Hi, Guy. My question is the distinction between it seems like the matrix is just given to you maybe with zero work. It's not really clear. And then the scalar equation requires some serious work, but I'm not, I mean, that is, once you've constructed G,
So
maybe there's automatically a matrix, or what's the compatibility that you need in order to?
So let's say I think in this case we use the green and the red. So let's say the fact that you have two sets of curves is allowing you to have two coordinates, and you can control the two coordinates, and then you essentially have something like two solutions to your equation, which are sort of conjugated, right?
Mm-hmm.
And the difficulty, so essentially I'm saying locally, when you're giving yourself two functions, such that, I mean, one is the level sets are perpendicular to each other, then actually there will be solutions to an equation of the type divergence A gradient with A scalar. And
So it's the orthogonality of the two sets of curves?
Of the curves gives you, if I compute right, if it gives you the fact that your operator is a scalar operator.
Oh, okay, all right, that's good. So it's orthogonality, but this is a 2D phenomenon then.
This is a 2D thing, yeah. It's pretty much a 2D thing.
So you don't have this in higher dimensions, or?
And the reason why, well, I mean, unless cheating, right? Because you could always take the product of a Cantor set by something else, or you could play games. But the way I see it, I think it's really 2D, which is easier for computations. And it's more fun. And one reason why I don't like so much the general divergence form operator is that quasi-conformal mappings can, if you have a picture which is okay, and you take its quasi-conformal image, you get another picture which is okay, and that seems to be too easy. So for instance, if you were asking a question about it,
especially in 2 dimensions, it's too easy.
Especially in 2 dimensions.
Well, I have to add though a humble point that many smart people, which I'm not counting, and less smart, which I am counting, have tried to do it in a quasi-conformal for a while. So it's not that easy.
No, but for instance, if you ask the question for a snowflake,
snowflake, yes, but for this one,
it would be obvious, right? You could send the snowflake to a line and send the harmonic measure on the line to the harmonic measure on the snowflake, and you would get an easy solution. So here, of course, there's no way to send the Cantor set QC into a line, so you have to divide something, but still, okay.
But even the quasi-conformal version was open for a long time.
So to understand that correctly, that means the lines don't have to be exactly perpendicular. They could be within an angle of each other.
Right, but they cannot be degenerate.
The first set of pictures, and actually this looks like things that we had been doing when where it was actually fairly hard to. And if the lines are not orthogonal, but they still make decent angles with each other, then you get quasi-conformal coordinates, and then you will get a solution which is a divergence form operator. And I'm saying the orthogonality is the way to get. You have to be more careful with the picture, but I claim this is the way to get. I think it's a Laplace-Beltrami operator on some geometry, right?
Okay, I think that maybe it's time. It's a good time to wrap up. Thanks all the speakers again, and so we enter the last part of the program, of today's program.